Assalamu alaikum everyone. In this presentation we gonna explain the final project of the semester for the course 30304. The title of the project was Arithmetic Logic Unit Design or ALU. So the team was, as you see, Afrin Akhtar Nika, me Julkarnain bin Ashraf and Muhammad Amir Ishtiaq. We all are from Department of Electrical and Electronic Engineering, Buret. At first I will try to explain the basic introduction to the project and also the relevant theories for the project, and then Muhammad Abrar Istiaq will explain the Proteus schematic design, and Afrina Anika will tell about the Verilog Code. So the aim of the project was to know more deeply the concept of ALU. ALU is a very important concept for building modern computers, and so in this project we have tried to implement 13 simple arithmetic operations. There are some other complicated operations, but we have implemented here 13 operations actually, because the complicated operations are not included in our complementary theory course. And as the software tools, Verilog and Proteus were chosen, and there are different kinds of ALU actually for bit 8 and others, but we have chosen for bit ALU as in this project we are taking 2 inputs for each case, and each input is containing 4 bits. And now, what is ALU? ALU is actually a combination circuit that combines many common logic circuits in one block, and that means that using a single block we can perform a variety of different arithmetic and logic functions, and these arithmetic logic functions can include arithmetic functions like addition, subtraction, multiplication and others, and also some other logic functions including AND or XOR, and NAND gates and others. And now if we say about the software tools, Verilog and Proteus. Verilog is actually a hardware description language, HDL. If you say about HDL is actually some kind of language in which designs are very easy to implement and debugging, and also normally very useful than schematics, especially for large and complicated circuits. So among these languages, Verilog is the most popular one used in semiconductor industry. And also if we tell about Proteus, this is also another software. It is actually electronic design automation software used in both educational and commercial environments. And in Proteus you can design a schematic with use of thousands of parts. And as I have told earlier that there were 13 arithmetic operations implemented in this project. As you see, there are 13 operations explained here: adder, subtractor, adder with carry in, subtractor with borrow in, and or XOR, NOR, NAND, NOR, and comparators like laser comparison, greater comparison, equal comparison. As we have seen earlier that there are different types of logic functions implemented in this project, but I will explain here just the truth table and circuit symbol for AND gate. And for other gates you can explore through prescribed books and other sources. And as you see here, the input, there are actually 2 inputs, A and B, and the output is 1C. So for different combinations of input we are getting different outputs. And also in the right side you see the circuit symbol for AND gate. And then if you explain here one of the arithmetic functions that will be implemented in the design. So we're choosing adder for explaining here. So you see the truth table and circuit symbol here. There are actually 2 inputs here, A and B, and output are 2, sum and carry. This is actually very simple. For different combinations of input we are getting different outputs. And also there are comparators, and here also input 2 and output there are 3, L, E and G. So this means actually lesser, equal or greater. So where the inputs are same, we are getting 1 in E, and where A is greater than B, we are getting 1 in G, and where B is greater than A or A is less than B, we are getting 1 in lesser one. And if you say about multiplexers, multiplexers are also very important for our project, as we will see how multiplexers are implemented here. Multiplexer is actually a combinational circuit that has maximum of 2 n data inputs, where n is number of selection lines, and from these inputs just one will go to the output defined as the selection lines. So here we see actually there are different types of multiplexers like 4 to 1, 8 to 1, 16 to 1. We are explaining here 4 to 1. As you see, there are 2 selection pins, S1 and S0, and for different combinations of selection pins we are getting different outputs. And multiplexers are also called mux as short form. We will see very often later. And 16 to 1 multiplexers are also can be implemented through using 5 4 to 1 multiplexers. And in this project we will use multiplexer to decide which operation will be performed in this circuit. So thank you very much. Later portion of Verilog and Proteus will be carried by Mohammed Abdul Istiaq and Afrin Akhtar.
Thanks to Julkarnain for the explanation of our approach regarding 4-bit ALU design. This is Anika here to describe the Verilog code and its simulation. We have made a code of about 13 operations related to our syllabus. Now in the code we have declared 4 inputs A, B, ALU cell and carry in, and input AB is of 4 bits and ALU cell is of 4 bits too, but carry in is of 1 bit, 0 or 1, and our output is ALU result and carry out. ALU result and carry out. Here ALU result is 4 bits too, but carry out is of 1 bit because the carries are always 0 or 1, and we have used an intermediate variable called temp in our code that is of 5 bits. In the always block sensitivity list, we have used A, B, ALU cell and carry is 2. That means all our inputs. Then we have used a case block in which we have set a specific value for ALU cell in a single operation, such as if I set ALU cell 0 0 0 0 0, it will conduct only addition operation, and if I set 0 0 0 1, it will conduct subtraction operation. And if we look more deeply in our code, you will see that we have used this TMP variable, which is an intermediate variable in our code, to make the A and B 5 bits by adding a 0 to the leftmost position of the input A and B, and the carry out is also the last bit or the leftmost bit after the addition result of 4 bits A and B. So in the same way we have designed 4 operations: addition, subtraction, addition with carrying, subtraction with borrowing, and each time the carry out will be the leftmost of the 5th bit, that is indicated by 10 4. Then we have designed 6 logic gates: AND, OR, NOR, XOR, XNOR, and they will work only for their specific ALU cell value. Suppose we have set ALU cell equal to 0 1 1 0, then the operation will be only XOR operation, A XOR B. And if I give 0 1 1 1, then it will be a logical NOR operation. So but in this manner we have designed the gates. And finally we have made a comparison of the input bits A and B by setting a comparison statement. If it's a laser comparison A less than B and this statement is true, then output will be 1. You can see output will be 1. And if A is not less than B, then the output will be 0. That means if our set statement is true, it will show the first bit, that is 1, and if not, it will show 0. Similar for the greater and equal comparison. If A is greater than B and is true, then the output will be 1, otherwise 0. And if A equal B, then the output will be 1 and otherwise it will be 0. And we have set a default expression for the overall code, that is A plus B. So here is our code explanation. Then we will show our simulation on Verilog. For the simulation part, I have set A, B, ALU cell 0010 and carry in 1. For this ALU cell, the 4-bit ALU will conduct the addition with carry in operation. You can see addition with carry in operation, A plus B plus carry in. So let's see the result. So I am saving this and simulating functional simulation. And this is the report. You can see the value of A 101, ALU cell 0010 and B carrying. So the result with carrying or the addition with carrying is 1111, then 1001 and carry out is 0. And the final result you can see it is 1001 with addition with carrying. Now I will conduct another operation using this. I will select ALU cell equal to 0100. Now let's see what happens. And 0100 is a logical AND operation. Let's see the result and match this with this. Simulator tool. Now you can see that here A equal to 0101 and B equal to 0011. 1 and 1 equal to 1, 01 and 0, 10 and 0, 000. So the ALU result is 0001 and is the AND operation of input A and B. Now we will see a comparison operation. For this we will see if A equal B or not. For this we will select ALU cell 1100. Let's see. We will select ALU cell 1100. Simulation successful and report. Here you can see A is not equal to B, so the ALU result is 000. If A would equal to B, then the ALU result will be 1. If I set ALU cell equal to 1011, then let's see 1011 is greater comparison operation. Save. Simulator 2. you can see A is 0, 1, 0, 1 and B is 0, 0, 1. So A is greater than B. As A is greater than B, the result will be 1. And here ALU result is 0, 0, 0, 1. So here A is greater than B and the statement becomes true and the result is 1. So here is the demonstration of the Verilog code.
Thank you to my fellow teammates of my group for explaining background theory and Verilog demonstration. Now I would like to talk about the Proteus simulation of our whole project. We can summarize the whole circuit into 3 sections, such as input, output, processing section. In the top side, you can see the input section. Let's see the input section more closely. Here, main inputs of the arithmetic logic unit are A and B. Here, this binary input is given from pressing the switch like this, and it is a 4-bit input, and A0 is LSB and A3 is MSB. Similarly, B possesses same property. In the right side, you can see comparator previous in. Comparator previous in is input to define previously state of comparator circuit. In the right side, you can see selector pin, and selector pin is for selecting among 13 operations we are doing. This selector pin is the representation of case conditional statement of our Verilog code. We will select among 13 operations which we are going to operate. Carry, and in the right hand side you can see carry and or borrow in, and this is for carry and borrow in input if you want to give any, and you can see carry or borrow enable, and you need to enable this if you want to operate any arithmetic circuit. Carry or borrow enable pin is used only if we want to see any carry out from the arithmetic logic unit. There is a dedicated 4-to-1 multiplexer to employ this condition for desired output. And here it is that dedicated 4-to-1 marks for enable pin. And you can see the marks where we can see only the carry out as output. After the input section, we need to get introduced with our output section of the circuit. Here you can see the 4-bit output, and here out 0 is for LSB and out 3 is for MSB. At the bottom of the output section, here you can see carry out output, and it is to be mentioned that here the block we have used is called Logicprobe big from the Proteus component section, and you can see here the component we have used, and it will turn into 1 if output is high, and it will change to 0 if output is 0. Now it's time to get familiar with our processing section of our circuit where 13 operations are done. You have already known from previous discussion the selector pin number for a specific operation. I am going to present all circuits in random order, as it won't be a problem, as output of each circuit is assigned accordingly. Now here you can see the circuit of AND logical operation. 7408 IC is used for this circuit. A and B input will get AND from here. Beside of this circuit you can see the circuit of NAND gate, NAND logical operation. You can see we have added a NOT gate after the output of AND gate. Just addition of NOT gate after the AND gate, and it is the NAND gate implementation. And 7404 IC is used as NOT gate. Now come to the OR logical operation. Circuit of OR operation is almost same as AND gate, just change of IC. Here 7432 IC is used for OR gate. Beside of that you can see the NOR gate. Similarly, like NAND gate, we will get NOR operation just after addition of NOT gate. Beside them there is a circuit for XOR gate. Here 74HC3H6 IC is used for XOR gate. Similarly, a similar case like NAND and NOR gate will be applicable for XOR gate. Just addition of NOT gate after the XOR gate, we will get the output of XNOR gate. The last logical circuit we have is comparator circuit. Here 7485 IC is used here for comparing two inputs. It can output whether the input A is greater or less than B or equal to B. Comparator previous input will be used here. The first arithmetic circuit here is error circuit. Here 4008 IC is used for 4-bit addition. Carry in is kept to 0 as we won't care about carry in this circuit. Beside this we have adder with carry in. This will take carry in into the account. So carry in is used and it will take the input we have given in carry in section. And here you can see adder. The same adder is used which was used in adder section. Just the carry in is the change between this circuit. The next circuit we have is 4-bit subtractor. This arithmetic circuit is also implemented using adder IC. Here you can see. The first adder IC is used to construct 2's complement of B input. NOT gate is used here for that purpose, for inversion to get 2's complement. And the second adder we have used which will add A with complement of B, which is actually subtraction of A from B. Our last circuit here is subtractor with borrow in. It is slightly different from simple subtractor circuit. Here three adders are used. First adder will add borrow in with B. Then second adder will do the inversion task like previous we have done in simple adder, simple subtractor. And the third adder will do the subtraction task from A to B. And after the whole operation, we will get the A minus B minus borrow in. The most important circuit of the whole simulation is 4 16 to 1 multiplexer circuits. We have to use 4 of them, as you can see here. 4 of them are used as there are 4-bit input and output, and we have to implement 16 to 1 marks circuit as we need to select among 13 operations through the selector pins. If you see single marks circuit, 16 to 1 marks circuit is constructed using 5421 marks IC. Here 74153 IC is used. 174 153 IC has two 4 to 1 mux circuit. That you can see, here is the first one and here is the second one, and here is the selector pin. And we use 3 IC here, as one mux circuit has two 4 to 1 mux, and another IC has 4 to 1 mux, and another IC we have used only 1 mux. Thus we have constructed a 16 to 1 mux circuit. Now we would like to demonstrate some of the circuits we have constructed with some specific input. As you have known previously about selection pin number, and we will select those operations accordingly. Now let us put the input A as 0, 1, 0, 1, and input B as 1, 1, 0, 0 from LSB to NSB. And let us put selector pin as 0. It will work as adder, simple adder. And here we need to enable the carry or borrow enable pin if you want to see any carry out bit exists or not. Let us see the output of simulation. And here you can see the output of simple adder, simple addition of that input. If we select the selector pin as 1, we will see the output of subtraction, and it is the output of subtraction. And here you can see carry out bit is 1. If we select selector pin as 2, then it will work as adder with carry in. Here you can see carry in, adder with carry in, output is this. If we input the carry in bit as 1, then we will see the change in output. Here you can see the change in output. And if we see some logical operation like OR gate, we have to select 1, 0, 1. Then we will see the, and now we need to turn off this as we are not doing any arithmetic operation. We will see the OR operation of those input, and here you can see the output. And if you want to do the NOR operation, we have to select this 7 selector pin, and here you can see the output of NOR, just the inversion of that NOT OR gate. And if you see the comparator operation, then we select once, then it will compare if those two input is equal or not. If it is true, then the LSB will turn to 1. As it is 0, you can certainly see A and B is not equal, thus they have not 0 LSB. And if we check the greater comparison, then we have to select 1, 0, 1, 1 means 11. Then we'll see if yes, you can see A is greater than B. Actually what it is, A is actually greater than B. So we are getting the desired output what we needed, and thus the finish, and we have demonstrated the simulation of our arithmetic logic unit project. For simple correction in our subtractor circuit, we need to add a NOT gate after the carry out pin of the last adder, and we need to edit both of the subtractor circuit, and then we will get the desired carry out output So from this simulation you can see now the carry out pin is right what we needed, and if you check with all of the possible input, then you will see the desired output. Through this simulation we would like to conclude the presentation of our project. Thank you for having patience. If you have any queries, feel free to ask us.